So in this video, I'm going to talk about the relationship between density and mass of an object. Now, you may have already experienced in either a chemistry or physics or any other kind of science class the formula or definition of density, which is equal to the mass of an object divided by the volume of an object. Well, I'm going to start off not by necessarily dealing with a bunch of three-dimensional figures. I'm going to start off with, kind of simpler shapes. And so the first one I want to talk about is a rod or a wire or a bar or some kind of one-dimensional object that has a uniform or constant density that we're going to call rho, which is again that Greek letter that looks kind of like a P just without the stem on the back of it. And that rho is going to be measured in mass per length. That is its units, is some measure of mass divided by a length. Then the mass of the rod or that one-dimensional object, whether it be a bar, a wire, whatever, it's going to be that density rho times the length of that object, the length of that wire, that rod, that bar, whatever it is. And so if we're given two different x values, we could do it as b minus a, or if we're just given the length, we would just do just x. Now, that's going to be pretty helpful because it's going to extend our idea into calculus a little bit better. Because what happens if we don't have, a constant density? What if it's not uniform throughout that object? So I say here, suppose a thin bar or wire or a rod or some other one-dimensional object can be represented by a line segment on the interval from A to B. Okay, and the density rho is going to be measured in that units of mass per length again. And what we're going to do is we're going to say that that rho, that density, is based off of whatever x value we know. And so I can find the mass of this object by actually integrating from A to B, from the start of that length to the end of it, so covering that whole distance. And I'm going to integrate the density rho of x dx. And so what this is actually doing is, again, saying if I have uh, this bar, this wire, this one-dimensional object from A to B, and its density changes along this, what I'm doing is I'm actually chopping this up into really small pieces of width dx, and I'm saying, okay, well, what's the density of just this little sliver, this little piece of the bar? And I'm multiplying it by the difference, that measurement, that short little length of the section. And that's what we're doing, is we're just adding up the density times the length of each one of those little sections and combining them all together in this one big integral. So hopefully this has prepared you a little bit better for what we're going to do in our example here. So we have a thin 2-meter bar represented by the interval from 0 to 2. Now that's really important to know what x values to use. And this is made of an alloy whose density in kilograms per meter. Notice again, kilograms is a unit of mass and meters is a unit of length. And it's given by rho of x equals parentheses 1 plus x squared and parentheses squared. So it's the quantity 1 plus x squared squared. And what we want to do is find the mass of the bar. So I'm just going to set up an integral. So the integral is going to go from 0 to 2. Those are my x values of 1 plus x squared squared dx. Now, I'm not going to want to try to do a u substitution here. I'm actually going to go ahead and FOIL out that 1 plus x squared squared, and that should give me 1 plus 2x squared plus x to the fourth dx. I can go ahead and integrate that like normal. So that will give me x plus 2/3 x cubed plus 1/5 x to the fifth. And our evaluation bounds are from 0 to 2. So I'm going to go ahead and plug in the 2, recognizing that if I plug in 0, nothing's going to, it's not going to add or subtract anything to this. It's just going to be 0. And so I've got to do 2 plus 2/3 times 2 cubed, which is actually going to be 8 times 2, which is 16. So that's 16/3. And then plus 1/5 times 2 to the fifth. Well, I just said 2 to the thirds was 8. So we're multiplying that by 4. So we should get 32/5. I'm going to go ahead and make a common denominator real quick. I think that should be 15. So that's going to be 30 over 15 plus 80 over 15. and I'm going to multiply that by 3, so that's 96 over 15. And if I add all this up, that's 110 plus 96, which should give me 206 over 15. Now we had units of kilograms per meter, and I integrated, and in this case, the dx is actually the meters. And so by plugging in 2 meters and 0 meters, that's going to help us get this along. So again, this was kilograms per meter as my rho. That was the density we were given, and I'm multiplying by meters. So the mass is going to be about 206 over 15 kilograms. And if I type that in the calculator, 206 over 15 gives me about 13.73 repeating kilograms. All right, so hopefully this helps you guys better understand the idea of how density and mass are related, especially for one-dimensional objects. Now, I will see you again in the next video where we talk about work.